Good morning. I'm Xiang Li, and this is Xiangyu Zhou. So today we're here to present a new, more efficient synthesis algorithm for programs with local variables. To start, let's see an example of a program with both local variable and data dependencies. So one that comes to mind immediately is fold, which is a very common higher-order function in many languages. So fold takes in 3 arguments: a list to fold over, the initial value of the accumulator, and then a lambda function that takes in the accumulator, the current element, and gives the new value for the accumulator. So we see that there are 2 local variables, ac and elem, and that the value of ac depends on the results of previous iterations. So there are data dependencies. Synthesizing programs like fold turns out to be very challenging. So several prior works have tried to tackle this problem using either bottom-up or top-down synthesis approaches, but all of them have to fall back to some form of enumeration in the worst case. And we want to avoid enumeration because it can be very slow. So we thought, can the classic approach of bottom-up enumeration with observational equivalence work for programs like fold? And unfortunately, it turns out that it's quite challenging. And Peleg et al. Summarize it as a chicken and egg problem, in the sense that the accumulator values are required to evaluate the programs. But on the other hand, we need to know the programs before we can obtain those values. To see this in an example, let's see a fold program, and let's execute it. So we see that we need to execute the first iteration to know that the accumulator value will be 7, and we will then be able to plug 7 into the second iteration to evaluate the second iteration. And on the other hand, we need to know the program has a body of ac times 2 plus 1 before we can obtain those accumulator values for each iteration. So we thought, how about like top-down if bottom-up is very challenging? Well, the most like naive top-down is you can sort of list all the potential bodies for the fold and just evaluate each of those programs separately for 3 iterations, and then check their output to see if one of them produced the desired output. But this is obviously very slow because this is just full enumeration. But we observe that there are some advantages that we can take advantage of many shared properties, because those subprograms actually share outputs within one iteration or even across iterations. So we thought this is a very good opportunity to apply observational equivalence for those bodies of the fold. That's how we propose the idea of lifted interpretation, which combines top-down interpretation of all programs in a grammar with a bottom-up enumeration, a bottom-up enumeration with observational equivalence. So here on the left, it's a very familiar top-down interpretation of all the subprograms in the grammar. And on the right, we construct equivalence classes of those subprograms from bottom-up. So this might sound a little bit abstract. So let's take a simple example. So those are the 2 fold programs we saw earlier, ac times 2 plus 1, and ac plus elem times 2. So we'll start by walking down the tree until we hit a terminal in the grammar, and then we're going to evaluate ac. So I want you to focus on the big curly brace on the right. So that's how we represent a context in the equivalence class. So the context now for the first iteration consists of 3 things. First is the list, which stays the same for all the iterations. Second is the current value for the accumulator, which starts at 3. And third is the current element, which is 2 for the first iteration. So this equivalence class on the right groups all the programs that produce the output of 3, given the current context. And currently, there's only one subprogram, which is ac. We can continue the interpretation and then see the literal 2, create a new equivalence class on the right. We can do the multiplication, create a new equivalence class of programs that output value 6 on the right. And then we can finish interpreting the first subprogram ec times 2 plus 1, create a new equivalence class of programs that output 7 on the right. Now we can continue this process for the second subprogram. And then we see that ec has already been seen when we evaluate the first subprogram, so we don't create a new equivalence class. And then lm also produces 2, but for clarity of illustration, we're going to separate them into a separate class. 2 is already seen, so we don't create a new one. And then lm times 2 produces 4. So that's a new output, so we need to create a new equivalence class. And lastly, we can finish executing the second subprogram. And we notice that it produced the same output as the first subprogram, namely 7. So we can merge that into the same equivalence class that we constructed earlier. So we notice that there are already plenty of sharing going on in the equivalence classes for this simple example. And we can continue this process for the second and third iteration.
Can you hear me okay? No. Oh, yes, okay. So we have illustrated on a small toy language for float function. And now we want to apply it to solve a more complicated real-world problem. So we chose a domain of web automation, where in this domain, the main task is to automate interactions on the web page. For example, to scrape a list of item price on some shopping website. This time we use the domain-specific language, which is much more complicated and bigger than the language in the previous example. And here are some important components. So programs in this language is a sequence of statements, or it can be a skip symbol when it is at the end of the sequence. A statement can be a singleton action, like a click, or it can be a loop procedure. That is commonly used to loop through a list of items and to apply actions on each of it. So as you may notice, we use the lambda expression to represent the loop body, which in turns introduce local variable in this domain. Finally, we'll have the selector, which is used within the statement to locate some web element. And the fact is that there can be tons of alternative selectors for each statement, which makes the program space to blow up very quickly. So this is also why this domain of the problem is very challenging to solve. So in synthesis problem, we use so-called tree semantics in this domain to evaluate our programs. That is, given a program and a context, it should give you back an action trace and a new context. And here's an example. So given one program in our language like this, there's one click followed by a loop statement. We will evaluate as following. So given an initial web page pi0, the first statement click will be evaluated on pi0 and output some web page pi1. And evaluating the second statement, the loop will start to iterate through a list of items. And within its body, we will continue on pi1, output some pi2, and at some point we will stop and output some web page pi_n. All the actions being acted will be recorded as an output action trace. And most importantly, you may notice that there exists a data dependency. So that is, one statement has to be executed under the context that is computed by evaluating its previous statement. So therefore, when we are evaluating programs with local variables in this domain, in other words, the loop procedure, we may again have the chicken and egg problem. So let me put up the previous program from the last slide again. So when we are evaluating the loop, when the first iteration starts, we will start on some input web page pi1 with a binding of the first, bind the local loop variable to the first item of the list. After the first iteration, we'll get some web page pi3, and when the second iteration starts, we will continue on pi3 with a new binding. So that is, one iteration also has to be executed under the context from its last iteration. So similar to the fold function example, we may not be able to reduce the space without considering the local context. So to address this issue, we applied lifted interpretation in web automation, which is to use trace semantics to create this context output pair to represent those equivalence classes of the subprograms. In this way, we build equivalence classes and evaluate programs simultaneously to reduce the space. And the whole procedure will be very similar to the one with the fold function. And we don't cover very detailed rundown, so we will recommend to you to read the paper for detailed algorithm in this application. So for evaluation, we used a set of 131 real-world benchmarks in web automation domain. And we implemented our approach in an artifact called Arborist. We compared against two other baselines where WebRobot is the state-of-art technique in web automation domain. And for setup, our goal is to ask the synthesizers to find one program within a 1 second time limit set for interactive program synthesis. So the result shows that our artifact can solve 93.9% of the total benchmarks, which is significantly more than the other baselines. And worth to mention, on the newly collected and generally more challenging benchmarks, we can solve 2.5 times more and use 6 times faster time than the state-of-art technique. So here's the final page for takeaway. We proposed lifted interpretation, which is to interpret all programs from top down and construct equivalence classes of subprograms from bottom up. In this way, we can efficiently reduce the space of programs with local variables. And we outperform the state-of-art technique to solve more benchmarks and use that time on the web automation benchmarks. We're now open to any questions. Thank you.
Questions?
Nice talk. So you evaluate on the web automation, but there's probably a lot of domains where you have things like side effects or loops or where this might be useful. Any plans to, expand onto other domains?
Yeah. So good question. So in this work, we only applied on web automation domain. So that's the only evaluation we did. But the message we want to convey, including using a small toy language for demonstrating our approach, is that our approach can be potentially generalized to any programs with use of local variables. And well, worth to mention, the programs with data dependency is something that's a very interesting case, but our approach is general, and we hope there can be more opportunity for evaluation.
Thank you for the great talk. I'm wondering whether, what would happen if you try to do local variables that are not defined by the higher order function? Could you handle assignments or maybe even arbitrary fresh variables, or is it going to stop you from terminating?
So our approach is general to all programs with local variables. So actually, we don't care about data dependency or like fold left or fold right, or whether it's a for loop. So like in our like web automation evaluation, we have actually two types of loops. One that's looping over a spreadsheet data column, and another is actually looping over the selectors on the website. And we also have a while loop actually. So it's like general to any sort of structure with local variables.
But do you need to know them in advance, or can you also do fresh variables when you enumerate?
Oh, so I believe we do need to know the variables. So it's like a lambda, you need to know the variables.
Makes sense. Thank you.
Yeah.
Okay, I have a question. So when you are using this data dependence analysis, how difficult it is for this particular domain, and what are the problems you see for the other domains in this case?
So we don't actually do analysis in the technique, but if you are like talking about the complexity of the web automation domain, then we believe it's quite challenging because basically there is dependency everywhere. So we have to know the web page of the previous action to do the evaluation for all the other subsequent statements. So it's sort of like a very good domain to evaluate our technique.
Okay, if there is no other questions, let's thank the speakers.